Dear students, we are starting a new topic. This is the same chapter, chapter number 3, kinematics. And this is displacement time graphs. In the last chapter, in the last topic, we remember we had a comprehensive discussion on the equations of motion. We learned how to derive the last two equations, the second and third. And we discussed some of the situations in which those equations can be applied. There are two conditions that always are required before you apply those equations. The object must be moving along straight line. That is why they sometimes use the term displacement, sometimes they use the term distance, because when an object is moving along a straight line, distance and displacement are same. The second condition is for the application of equations of motion, acceleration has to be constant. So there will be no situation in your past paper questions, you won't see any question in which acceleration is variable and they ask you to apply an equation of motion to work out any displacement or any velocity or any time taken before an object moves from one place to another. So it has to be a constant acceleration all the time. Displacement time graphs, as the name suggests itself, is how an object is changing its position from a given reference point, because displacement means some initial position to another position. So if an object is changing its position with respect to a certain reference point, with time, there could be different shapes of displacement time graphs, obviously. We'll discuss some special cases to understand, because they are the typical ones that we have in the exams. So let's see what it means to means about the motion of an object if displacement time graph is a straight line. This is the simplest of all the situations. This displacement time graph simply shows that an object initially is at a certain position and we take it as an origin. And from this origin, it changes its position with time. And that means it goes away from it and equal distance is covered in equal intervals of time. That means if this scale, let's say, is in meters, and this is 2 meters, this is 4 meters, this is 6 meters, and let me write it big so you can read it carefully, clearly. 2, 4, 6, 8, and let's say this is 10. 2, 4, this is 6, and this is 2. So you have a scale on this side and you have a scale on this side. Let's say this is in seconds, and after 20 seconds an object has covered approximately 6 meters. The object must be moving along a straight line because equal distances are being covered in equal intervals of time. So the object is moving at a constant speed or a constant velocity. Again, the difference between speed and velocity is blurred here because the object is moving along a straight line. So they might call this a distance displacement, a distance time graph, or a displacement time graph, because it doesn't matter. The important thing is what other quantities can we calculate from the displacement time graph. So one important quantity that we can learn from displacement time graph or distance time graph is speed or velocity. That simply means the gradient of this graph, whatever its shape, gives us the speed or velocity. Speed if it is distance time, and velocity if it is displacement time, because we'll take care of we are particular about the terms. Distance, let's say this is distance on this side and this is time on this side. So clearly speed of the object is constant, because clearly it is the constant gradient everywhere. So this is 6 divided by 20. So 6 meter divided by 20 second gives us something like, if I cancel this 0, this should be 0.6 over 2, something like this. And if I further cancel this with 0.3 meter per second. So this is the speed with which the object is moving, and this is a constant speed. But obviously there are other possibilities. Let's say after moving at a constant speed for initial 20 seconds, the curve is something like this. And then it gets straight. What has happened during this time? There is a curve now. So remember, whenever you have a curve like this, and this is, by the way, a curve which shows this shape. So whenever you have a curve like this, like a sad face, this simply means the speed is decreasing. The speed is decreasing because the gradient is decreasing. So speed is decreasing from this position if I label it as A and then I label it as B. So speed is decreasing from A to B. This is decreasing speed. Decreasing speed. And what is going on here? I mean, if this is 30, 40. From 20 second to 30 second, during these 10 seconds duration, the speed has gradually decreased, and then the object has come to rest at B. So B shows rest because after that there is no change in position with time. So for the next 10 seconds after the speed gradually decreased, the object remained at rest. But then if it moves like this, what does this mean? This is a curve, like you have a curve on the happy face. That means the speed is increasing now gradually. So there are 4 different types of curves on the displacement time graph. One curve is a straight line but with non-zero gradient, then a curve as you have on the sad face, then a straight line but with 0 gradient. This is a straight line and this is also a straight line, but you know the difference. This is 0 gradient, this is non-zero gradient. And there are 2 types of curves. One is a curve as you have on the sad face, and one curve which is like this, which is on the happy face. Sad face means the speed is decreasing, and this happy face means speed is increasing. Speed is increasing gradually. And we'll always assume, and there is a reason to assume this, if this decrease in speed or increase in speed is gradual. This is a smoothly varying curve. It's not an any haphazard or any you can say unstructured kind of shape. There are no kinks here, there are no ups and downs here. It is a smoothly varying curve. That means this is decreasing speed, means there is a deceleration involved here, and this is increasing speed, so there is an acceleration involved here. So this means it is a deceleration and this means an acceleration. This means that when you have a curve on the sad face, your speed is gradually decreasing. That means there is a deceleration involved. The object is slowing down gradually. And if it is a smoothly varying curve, we assume that this is a constant deceleration. As I said in the beginning, equations of motion are also applicable if you have a constant or constant acceleration or constant deceleration. So most of the time these curves will be smoothly varying curves, and if there is no smoothly varying curve, there will be ample explanation for that. There will be hint about that, what's going on there. But as long as this variation is concerned, this should be understood. You should know that this simply means a constant acceleration because speed is gradually increasing, and this increase is apparently uniform because the gradient is uniformly increasing. Here the gradient is uniformly decreasing. So speed can be calculated from the gradient of it, and if you have to state in words what is happening to the motion of an object from the graph, and you have a curve there, you can use the word deceleration and acceleration instead of increasing speed or decreasing speed. So this is the displacement time graph. But what if the displacement time graph goes down? Let's say at some stage this graph comes like this. Let's draw that type of graph on this side. Suppose suppose a graph is like this. What does this mean? This simply means that an object is initially at a large position from a certain reference point. So initial displacement is not zero. X, if it is measured in meters, time, if it measures in seconds, now clearly shows that the object is coming towards this position. It is coming towards this position, and it is moving at a constant speed again. And this speed, if it happens to be a velocity now, clearly this will have a negative sign because this is moving opposite to, maybe initial direction is like this, and now it is coming back to the initial position. So this means the initial position is non-zero. It might be 10 meters away from the initial position, and now it is coming back to that initial position. And if in same intervals of time it covers equal displacement, that means this is constant velocity or speed with which the object is coming back. The object is coming back or returning to the initial position. So whether this constant velocity is large or small will be decided from the gradient, obviously. If an object starts from the same position, but it covers all this distance in smaller time, obviously it is moving faster. So if it has a larger gradient, although negative gradient, but larger value, larger magnitude, that means it is moving faster in order to come back to its initial position. So these are 1, 2, 3, 4, 5 different situations that you can describe in words if you have a displacement time or distance time graph in the question. Let's move on to the velocity time graph. We'll refer to these graphs again and again. We'll relate if velocity is changing in this manner, how should displacement be varying. So you will have a chance to revisit these graphs again and again in the discussions that we have in this lesson and the next. Speed time or velocity time graphs. Again, there are various situations, but in order to remain or have a focused discussion, we'll discuss particular situations. We can discuss special cases so we understand what type of graphs we have in a given situation, and these are the situations we most of the time have in the past paper questions. For example, what should be the velocity time graph of an object if it is moving at a constant velocity? One situation in which an object is moving at a constant velocity is the one when a car or a train or a plane is moving at a constant velocity or a constant speed along a straight line in a given direction with no acceleration in it. That graph is something like this. This is constant velocity. An object is moving at a velocity which is not changing in time. This is velocity measured in meter per second most of the time, and this is time axis measured in seconds. You will see most of the time units are not mentioned because perhaps that doesn't matter much as far as the shape of the graph is concerned. It could be any units, and if you can understand what this shape means, then without taking care of the units, you can describe the way the object is moving. So object is moving at a constant speed, or you can use the word constant velocity. So a straight line, obviously if this is a line here, then it is a constant velocity of larger magnitude. If this is a line here closer to this axis, then obviously it is, but what is this line about? This line, which is a non-zero gradient, again a straight line, but non-zero gradient rising at a certain gradient means the velocity or the speed is now increasing at a constant rate. So this is the same thing that we had in the displacement time graph as a curve. The curve which was on the happy face, that was the constant acceleration, and on the velocity time graph it's a straight line with a non-zero gradient. So this is increasing velocity or constant acceleration. This is constant velocity, but this is constant acceleration. Constant acceleration means velocity is not constant, it is varying now, but at a constant rate. We also use the word uniform acceleration or constant acceleration. And for constant velocity, we use the word uniform velocity. When it's a uniform velocity, acceleration is zero because there is no variation in velocity. When acceleration is constant, that means velocity is varying at a constant rate. So it has to be a straight line. What if this curve comes down like this? This is again a straight line, but it has a negative gradient now. This means a deceleration. That means velocity of the object is now decreasing at a constant rate now. It's not about the position now. It doesn't mean the object is coming back to its initial position. We don't know. But this is about decreasing speed gradually. So constant deceleration. That may means that an object initially moving in this direction has applied brakes and it still continues moving in the same direction. It is not about the change in direction as we saw in the displacement time graph on a graph like this. This is simply an object slowing down. So it could still be moving in the straight line in the same direction, but it is slowing down as it has applied brakes. It could be a train which has applied brakes, and in this amount of time, this is the time interval in which the object has gone from this speed to zero speed. That means it has stopped here and it remained at rest for all the time that follows on this scale. This line means the object has remained at rest for all the time after this. So it was moving initially for this time. We can read this time from the scale and easily describe that object was initially moving at a constant velocity or with a constant speed for this time. Then for this time interval, if I label it as T1, this is the interval T1, this is the interval T2, this is the interval T3, and then this is the interval T4, and so on. So what happens during T1 is obvious. What happens in T2 is also obvious. What happens in T3 is it has a constant deceleration. The object has applied brakes and it finally has come to rest here. And in time interval T4 and after, the object has remained at rest. So two quantities which we can easily see, we can calculate from a velocity time graph is, number one, we can calculate acceleration from the gradient. Acceleration is gradient on a velocity time graph. It could be a positive gradient, means velocity is positive, that indicates one direction usually. But if the values of the velocity are on the same side, I mean velocities are not negative, they all have positive values here, that simply means the object is slowing down but it is not changing its direction. But you will see, if I have a velocity time graph in which the object is initially moving with a certain velocity and then it applies brakes and then it comes to rest, then what if this graph continues on the other side of the graph? That means the object, after coming to rest here, changes its direction and then continues with the same acceleration, because this is the same gradient as this. So while this is the change in velocity, but the object is moving in one particular direction, this is the same rate of change of velocity, but the object is moving in the opposite direction. So a certain constant acceleration, with the velocities positive. Velocities are positive. This is also same constant acceleration, but now velocities are negative. That means the object is now moving in the opposite direction. It's the same acceleration, but this direction has positive values, all of them, and this, when the object has started moving in the opposite direction, the velocities are all negative now, because this scale is showing you the values of velocity. So if this is 5 meter per second, 10 meter per second, 15 meter per second positive, when the object is moving in the opposite direction after slowing down, coming to rest, and then it continues in the opposite direction, then this is increasing. So yes, you might call it deceleration and this as acceleration. This graph could also be drawn in the opposite sense. It could be something like this, but it will have the same meaning. The object is initially having negative values that indicate one direction. The object is initially at 15 meter per second, then its velocity decreases, then it becomes 0. So this could be a deceleration, ultimately going to 0 velocity, and then the object moving with the same acceleration but in the opposite direction. That means the velocity changes direction and the object starts accelerating. So velocities have started increasing because this is 5, this is 10, this is 15. So if this is a straight line like this going from one side to the other, this simply means the object is undergoing an acceleration of constant magnitude, but its direction is changing. So we bring velocities from positive side to negative side or from negative to positive side. Either way, it is considered correct. So this is the introduction of a few situations of velocity time graph. But let's make it more specific. Suppose we want to know the shape of the graph, velocity, let's simply write it VT graph, PT graph for an object dropped from a small height. Dropped from a small height. Now this word is important. If the object is dropped from a small height, a few meters, an object like this is dropped from here or from a few meters above this, air drag, air friction can be ignored, and that simply means the object will move with a constant acceleration. There will be no obstacle to its motion. Air will not have enough friction to offer. So the object starting from initial velocity 0 because it is dropped. If an object is dropped from any height, initial velocity is always taken 0, and this is the constant acceleration with which the object falls. So if it's a freely falling object, its acceleration is the gradient of this straight line, which is 9.81 if you accurately calculate this. But what if this height is not small? If this is a very large height, then the situation changes. From a large height means now the air drag cannot be ignored. So instead of moving as a straight line, this line, soon after it starts falling, starts to take this shape, and then it becomes a straight line like this. So initially, it's not possible to distinguish between the two situations, whether the object has constant acceleration or it's variable. It's not easy to tell. During the first few seconds, the object falls as if uh, it's falling from a small height. But soon after, this curve shows that its acceleration has started decreasing. Now this is important. On a velocity time graph, a curve like this, as if you have on the sad face again, this means decreasing acceleration. Decreasing. Now this is not decreasing speed or velocity, this is decreasing acceleration, which means the object still has acceleration, its speed or velocity is still increasing, but the rate at which it increases is becoming small and small and small. The increase in speed is not that large now. So it gradually, uh, gradually decreasing acceleration means the increase in its speed becomes smaller and smaller. The rate at which it was increasing initially was 9.81, then it may become 7.5 maybe, then it becomes 5.2 maybe, then it becomes 2 point something, that becomes 1.1, and finally there is no more increase in its speed. So this is zero acceleration. That means it becomes constant velocity. This is the situation when the object is allowed to fall from a very large height. Then it is not a straight line anymore, although it is starting from zero velocity, although initially the acceleration appears to be 9.81, but a few seconds after it has fallen, it acquires sufficient speed that makes air drag significant, because air drag is the kind of force that increases with speed. So if initially the object was moving slowly, air drag was not that significant, but as the object acquires larger speed, air drag becomes more and more significant. So due to the more air drag, there will be larger opposing force in the upward direction. So acceleration will become smaller. Object will not be able to accelerate that much. It will not be able to accelerate freely. Its acceleration will decrease, and ultimately the air drag will become such a large force that it balances the weight of the object. This is something you have learned in your O-level classes. I'm only repeating it because there are questions in the exam related to situations like this. So a well-known name for this velocity is terminal velocity. So terminal velocity is that velocity of an object, if it's falling freely, for example, where weight and air drag become equal. If it's a situation of a car moving on a straight road, it tries to accelerate at that road. Its speed goes on increasing initially at a constant velocity, constant acceleration, but then air drag becomes such large force opposing its motion that its acceleration actually starts decreasing, and then there is a very large speed in the end beyond which it is not possible to go, beyond which the object, the car or the plane or the train cannot increase its speed any further. That is the velocity, the terminal velocity, the kind of velocity beyond which you cannot go in a medium. So this is it for today. I will have many more situations to discuss on Wednesday, inshallah. Until then, you go through all this, listen to this discussion carefully, and if you have any questions, we can have today's session, and in the next session, you can ask the questions. Thank you.